Welcome back everyone on the day 11 of this online seminar. And our first speaker for today is Professor Pranav Pandit from ICTS TIFR, and he will be speaking on duality in higher categories, part 3. All is yours, Pranav.
Thanks. So let me just begin by, I have a couple of things to say. One is that Shrikant reminded me to upload my lecture notes, which I've done. I've also corrected a couple of errors that I noticed in the notes while going through them. So maybe I should just mention what they are, so that when you're reading, you can look for them. One was that I think I wrote that E infinity algebras in simplicial sets. What am I saying? E infinity simplicial abelian groups. E infinity algebras in simplicial abelian groups correspond to commutative DGAs in characteristic P. So the statement characteristic 0 was that simplicial rings, commutative simplicial rings, correspond to commutative DGAs, which are connective. The corresponding statement in characteristic P is that E infinity rings in simplicial abelian groups correspond to E infinity rings in DG algebras. Whereas I think I wrote something slightly different. On one side, I wrote commutative. I could have put commutative on the simplicial side, but I think I put it on the wrong side. So it should be E infinity on both sides to be right. And the other statement that, again, I don't know if I said it right, but in the notes I had written that K-linear stable infinity categories correspond to DG categories. That's true with a qualification. So you need to work with triangulated DG categories. So there's a notion of triangulated DG categories, and those correspond to stable K-linear infinity categories. So yeah, just a couple of caveats that I think I should mention. In any case, I haven't gotten into any of the technicalities in these talks. It's more to give a sort of overview of the ideas. And of course, if anybody has questions, I'm happy to, of a technical nature also, we can discuss them in the discussion session. Okay, so let me continue with something I had intended actually to say much earlier, but the general framework took a bit longer than I expected to discuss. So today I want to start talking a little bit about dualities. In the final lecture, we will really pin this down. So the goal is to describe a theoretical framework for describing a class of what you might call duality phenomena. Okay, so whether or not that includes what you're interested in as duality, that's a question of language. I'm going to describe a certain class of phenomena that you might legitimately call duality phenomena, and hopefully I'll convince you that higher categories provide a useful framework to think about these things. So let's begin with the question, what are dualities? So a heuristic answer, as I said in the first lecture, you might say that you have a duality when you have different descriptions of the same of a given underlying phenomenon or a given underlying entity. Right? When you have two different descriptions, you might say they're dual descriptions. And you can go back and forth between the two descriptions. So here's an example, which I mentioned already. You might think of something like Fourier duality, which is a special case of Poincaré duality, where the duality is the purpose of discussing something like this is that it's familiar to everyone. So you have L2 of S1 and L2 of Z, and you can think of the elements in Z as labeling characters. So they're homomorphisms from S1 to C star, and those are given by chi n of t is e to the power 2 pi n t. Right? And the duality says that if I can repackage the information of a function on an L2 function on S1 as a function on Z, where the new function f hat is given by this formula. F hat of chi n is this integral. So we've completely, if I just hand you f hat of chi n, that's just a list of numbers, and somehow this list of numbers, has the information required to reconstruct this function, and you can go back and forth. And this is an example of duality where you have two sets being matched up. You have a bijection of sets, and in fact, there's more structure on these sets. These are Hilbert spaces, and you have an isomorphism of Hilbert spaces and so on. So in any case, the point is that this lives at the level of sets, right? I have two sets, and I can identify these two sets, and there's a specific map which identifies them. Now, before moving on to other things, I just want to note a feature of this map, of this Fourier transform, if you like. The way it works is it's part of a general paradigm, which you might call the pull-push paradigm. which is that you have a following setup. You have a space Z, which maps to two spaces X and Y. If I'm in this situation and I look at functions on X, I can ask, can I map that to functions on Y in some natural way? Now, suppose I give myself the data of a function on this correspondence, I mean on Z, which is so such a diagram you might call a correspondence. It's basically a relation between the two sets. It's a subset, you might think of this as some Z mapping to the product X cross Y. So if I start with a function, so f of Z for me denotes functions on Z. What kind of functions will depend on what you're interested in. It might be L2 functions, C infinity functions, holomorphic functions, depending on the context. But in general, you can do the following thing. You can pull back a function from X to Z, multiply it with K, and then push it forward along the second arrow. So pulling back is exactly what you think it is. And pushing forward is what we call integration or summation. Right? So how do you push forward a function on Z to a function on Y? You simply sum over the fibers of P and you get a function on Y. So this is an example of pull-push because you're pulling back a function from S1 to S1 cross Z and you're multiplying it by e to the minus int on the n component here and then integrating. So here's another familiar example of this. If I take X and Y to be finite sets, then pulling and pushing like this recovers matrix multiplication because functions, say complex valued functions on a finite set, they form if the set has cardinality n, they form a vector space of dimension n. Then I can pull it back to X cross Y. So if Y has dimension m, cardinality m, then X cross Y has cardinality n cross m. I can take a function on n cross m, which is nothing but a matrix, multiply and then push forward, which is sum. So you can exercise is to check that matrix multiplication is nothing but push-pull in the context of finite sets. So it turns out that this is a very useful sort of blueprint for thinking about how you map certain objects on some space to an objects on another space. Right now I'm talking about functions, but later you might want to categorify and talk about things like sheaves. And later you might even want to talk about sheaves of categories or whatever, but the general framework remains the same. Okay. So now let's move on to some of the things that you've already seen in this course, in this winter school. And my goal is to sort of package them into a kind of common framework, at least to some extent. So we've seen Poincaré duality, which let's say I could discuss this in at various levels of generality, but let's say M is a smooth, compact, oriented manifold without boundary and of dimension D. There are generalizations to when you have boundary and so on, which I won't talk about, at least not now. So then, well, let's sort of approach Poincaré duality from a very naive perspective. What's sort of the simplest thing we might do is we might try to count the k-dimensional holes in this manifold, which we know mathematically we can describe that in some way as, say, the Betti numbers will give you a count of the k-dimensional holes, right? The bk of m. And then you discover that bk of m, the k-dimensional holes, are always the same in number as bd minus k of m. Right? You count these Betti numbers and you find that these always match up. Or you might discover you might start out discovering a shadow of this, which might be something like computing Euler characteristics, the alternating sums of these Betti numbers. And you find that for, say, odd dimensional manifolds, they vanish or something like that, which will be a shadow of this statement that bk of m is bd d minus k of m. So first you discover this, but then soon you realize that you can't do very much. You're sort of constrained in what you can do by just saying that two numbers are equal. Right? Just knowing that this number is equal to this number tells you something interesting, but there are many calculations and things you'd like to do which are simply too hard to do with, or you simply don't have the tools to get your hands on them if you just talk about numbers. Then you realize, and this is what you might call categorification, you realize that, well, actually bk of m counts something. It counts the dimension. When you say it counts the number of holes, it really means that it counts the dimension of some vector space. And that vector space is the k-dimensional cohomology of this manifold. Okay, so I'm choosing to work with cohomology and real coefficients. That's just for simplicity. I mean, you can do all this in much more generality, as I'll mention later. I can replace R by any sheaf, any locally constant sheaf and so on. That's hardly that's not sort of central to my point. So you have these Betti numbers, and these things count the dimensions of some vector spaces. And you can ask, does this equality of numbers really come from a map of vector spaces? And in fact, if you look at the proof of Poincaré duality, what it really tells you, and this is now take 1 on Poincaré duality, that was take 0, is that there is a perfect pairing between the vector space hk of m and the vector space hd minus k of m, meaning a bilinear pairing between these two vector spaces, mapping them to R. And this is induced by the choice of, not the choice, by the fundamental class of M, right? So integrating against the fundamental class is what induces this. And this is what you might call the Poincaré pairing. And this is a perfect pairing, meaning that it identifies hk of M with the dual of hd minus k of M. So look what we have done. Well, earlier we just had an equality of numbers, but that equality didn't tell you how the objects that those numbers are counting were being identified. But stating it in this way tells you that how we are identifying hk of m with the dual of hd minus k of m, right? So it really tells you much more information. Now, this is still deficient in some ways. This is deficient because we're working with cohomology classes, which are equivalence classes of something, and we have identified two cocycles if they're cohomologous, right? So again, you can ask, can I refine this to a statement that actually is a pairing at the level of the cocycles themselves? Again, it's of the same flavor, because here I've declared two things to be equal. And remember, the slogan from my previous lecture is that you're not supposed to declare two things to be equal. That leads to loss of information. So this was a very brutal way of declaring two things to be equal. We simply just forgot about the objects. Just remember that the dimensions of the objects are the same, are equal. This is a slightly less brutal way, but we realize now that these objects themselves are constructed by identifying certain things. So we then ask ourselves for a pairing at the level of cochains. And in fact, if you again examine the proof on duality, you see that actually what you've done is to construct a map at the level of cochains. Oops, that should be a cup product, not a tensor product. Just hang on a second. This should be a cup product. And you realize that, well, I should have had I can actually define something at the cochain level, right? And this is also perfect in a certain derived sense. It's a perfect pairing of cochain complexes. You can incarnate this in the Duran model for cohomology, if you're working with real coefficients, as the pairing of ak of m, which is the k forms. This is k forms, smooth k forms, with the smooth d minus k forms, and that's just wedging together a k form with a d minus k form and then integrating over m. So we have this chain level construction. And this thing actually respects differential. So I could have written this as, maybe I can write it over here as dot c dot and c dot minus k. Okay, fine. And then you also saw in Samik's last lecture that you can actually refine this to a spectrum level construction. So C dot of M is sort of a linearized construction where I'm looking at, this is a model for something, namely its cohomology groups compute the homotopy groups of the mapping spectrum from M into the Eilenberg-MacLane space, into HK.
Oh, you mean D minus dot.
Oh yeah, sorry, D minus dot. Thanks, Samik. Thanks a lot. Yeah. So either of these things here is really a model for like mapping M into the Eilenberg-MacLane spectrum, and you can refine this to a statement. Now you can ask, well, I can do this at the level of cochains, but can I do something that works not over some ring, but really works in a purely topological way? And that would be the spectrum level refinement of this whole thing, which is what which you've already heard about. Now you can further ask, so we went from number to vector space, and from vector space to cochain complex, and from cochain complex to spectrum. And now you can ask whether all these things, the cochain complex level pairing or the spectrum level pairing, is this the shadow of something more primitive? Okay, so I'll try to make precise what this could be. But first, let's see some other examples where you have similar phenomena in other areas of mathematics, where again you climb up from something very basic and you find that you end up with something. You climb up what I call the categorical ladder. So I'll describe that later. So again, let's do cell duality, and again let's start with a simple case. So let's start with, say, a smooth, proper algebraic curve over C. So that's a Riemann surface for those who are not so familiar with algebraic geometry. But now you've seen it in Suresh's lectures. So, and let's fix some divisor in X, which just means a finite formal sum of points in X. Okay, so I've chosen finitely many points, and I've assigned some weights to them. The weights, I've taken them here to be, say, non-negative, just for fun, but I could take negative as well. So this is just a formal combination of points. If you want to, you can take all the coefficients to be 1. So I have like finitely many points in X and a weight 1 attached to each point, if you like. So then I can study something like so you might be interested in holomorphic functions on your algebraic curve. And they're not many. In fact, they're all multiples of the constant ones because by the maximum principle. But you can find holomorphic sections of other line bundles. So for example, you can ask for holomorphic 1 forms, which are sections of the cotangent bundle of C, which is a 1-dimensional vector bundle. And you can ask, well, how many linearly independent holomorphic 1 forms are there which vanish to order AX or more at each point X? Okay, so they vanish to order AX at X, and there's no condition outside. They're holomorphic everywhere, and they vanish to order X. That's a very concrete question. And you'd find that this is in bijection, or sorry, the number of these sections is the same as the number of linearly independent meromorphic functions with poles of order at most AX at each of the points X. Now that's an interesting fact, right? I mean, that's something that is not obvious, but it's true of any Riemann surface. I mean, it's not obvious unless you know cell duality or something sophisticated. And again, you can ask the same question. Well, I have this equality of 2 numbers. I count these things, and I always find them to be equal to the count of these other things. But is there a map that implements a map between the vector space of holomorphic 1 forms vanishing in a certain way and the vector space of these meromorphic functions that implements this this equality? And in fact, there's a perfect pairing which goes between you first recognize that the oops, sorry, I wrote H1 where I should have written H0. Let's go up something. Yeah. Hopefully I'm not messed up anything here. Oh, I think I may have messed up something here. Just hang on a second.
Yeah, the D.
What have I done wrong?
That.
I think I need a correction. Let me just check my notes. Just give me a second. Suresh, do you want to help me out?
Yeah. H0 of that's okay. No, H0 X OX plus T maybe. I mean, you want. That's one thing. And
well, let me just check my notes. Just a second.
HI and the other one is H. Yeah.
One of the D should be a plus and not a minus, right? It's a
Yeah.
dual
One of the D should be plus.
The Serre functor is suspension of omega tensor, the dual of. So.
Yeah,
that's what you wrote, right? At most and at least. So should be plus T. One of them should be a plus T.
No, I think my verbal description is wrong here. So this is correct, right? So this bottom row is right. This is said duality.
No, but the D.
No,
But this description is not right.
Acha.
no, it's both H0, I think, for the curve case, because remember HI and HD minus I. Oh, yeah.
It's
And if
0
you
and
put
H1. And
yeah,
oh yeah, and this
yeah.
should be a plus. One of these is a plus.
Correct.
Yeah, yeah, that's one.
This is a plus. I'm terribly sorry. So what happens when you write down stuff in a hurry? And this should not be number of linearly independent sections, but this should be like number of linearly independent one-check cocycles. Okay, this is a bit contrived, but I guess it's still something you might compute. One-check cocycles with values in meromorphic forms. With poles of order D, order AX at X, at least AX, sorry. At most AX. Okay. Yeah, the problem was with my verbal, with the sort of sentence description here. Is it okay now? Is everyone happy with this? I mean, this statement is definitely right down there. So this is just the verbal description of that. Suresh, are you happy with this? Or Shrikant?
It looks okay, yeah.
Yeah, I think it's right now. Yeah, so this was right, and this thing is what I have to fix. But in any case, my point is that the statement like this, that you have this perfect pairing, is really a statement about counting certain things, counting some very explicit things. And you might discover these things by first counting something and finding that the number of certain things, holomorphic one forms with some behavior, can be described as meromorphic functions on some check, on the one check cocycles of meromorphic functions with some particular pole behavior. But now we promoted this to a pairing on vector spaces, that you have a pairing from H0 of x, omega 1 of x minus d. This is nothing but holomorphic one forms vanishing along d. And these are exactly one check cocycles of meromorphic forms with poles along d. And so I have this pairing to C, which is the Serre pairing. And this is what Suresh described in his talks. Now, I can interpret this is a special case of the Serre pairing. More generally, if I have a holomorphic vector bundle, then I can say compute the sheaf cohomology instead of check cohomology. I could compute it using Dolbeault cohomology, which is the cohomology of this complex, where you take 0k forms with values in E, and you look at the Delbar operator acting on it. You take the kernel of that, divide by the image. That's a complex. So when you do this, you get the cohomology of E. Sorry, this is a complex which resolves E. So you get the cohomology of E in this way. And with this description of cohomology, I can describe this pairing explicitly as the pairing which takes alpha and beta to, integral of trace of alpha wedge beta. Well, in this case, it's just alpha wedge beta. So this is just the integral of, so this pairing over here is just alpha beta goes to integral over x of alpha wedge beta. And more generally, if E is any holomorphic vector bundle on any smooth projective variety, I have a pairing which is from the mapping space from OX to E, which is nothing but the cohomology of E, H0 of XE or HI. The ith cohomology of this mapping complex is exactly HI of E, tensored with the mapping complex from E to omega x to C. So I have a natural pairing, and the pairing is alpha tensor beta goes to integral of trace of alpha times beta. So if I multiply alpha and beta, I get a section of omega x with values and endomorphisms of E. Oops, again, I think I may have messed up. Have I written it right? Yeah. And so this is the integral of the trace of alpha times beta. Again, I think I've E and E dual, right? So E tensor E dual. Yeah. And this pairing is a perfect pairing. Any questions? So yeah, yeah, I just want to be careful that I've written it right here. So 1 second. So I taken, I mean, I hope it's clear what, well, I guess what's hidden is what is alpha times beta means. So this is a section of E, this is a section, I don't really need the trace, it's just alpha. The way I've written it is just integral alpha beta. Right. So this is a perfect pair, right? So the exercise is to check that this is what Serre duality says, right? So Serre duality, as was described by Suresh, this is what it's saying. Sorry. Okay, I'm having some technological issues. Yeah, I've moved to the right side. Good. So so here's the question again. So previously I asked if Poincaré duality is the shadow of something in the ways that we have formulated is the shadow of something more primitive. And again, I can ask this, is this pairing the shadow of something more primitive? Okay. And here's a hint to the answer that the very formulation of Serre duality as this pairing between mapping spaces in the derived category. So this mapping space is in the derived category of this is the mapping space. I've written it over here. This mapping space is our Hom in the derived category of sheaves. So there's a more general version where instead of EF, maybe I should write it in the general version. I think that's going to be even better. Let's say E and F are holomorphic vector bundles. Then I can do this more general thing. Then you really need the trace. So let's do maps from E to F. And here I put maps from F to E tensor. E tensor omega x. Now the special case that I wrote earlier, and now I need to put the trace. That's why I put the trace of A alpha beta. So what is this map? This map is just composition on the maps, on the mapping spaces, followed by integration. So if I compose, what do I get? I get a map from E to E with coefficients in omega x. I take the trace on the mapping space part, and omega x is a top form, so I can integrate it over M, or x in this case, integrate over x. So I get a number, right? So that's what this map is. And the special case I'd written earlier was where E is OX, F is some sheaf. So then maps from OX to F, tensor maps from F to omega x, maps to C. That's the special case that I'd written down earlier. And this is the general one. So maybe it's better to just have the general one. So I can just mention, okay, maybe I should mention that as a hint to the exercise. So for the hint to the exercise, let's go down here. So the hint here is take F E equal to OX. Right. So really, so Serre duality is this. This is what it's saying. And this is almost in the form that Suresh had described it. It's almost the same thing, what I've written. Modulo this, taking E equal to OX. Now the question is this a shadow of something? And already there's a hint that it might be, because we've been climbing the categorical ladder. I haven't made that explicit yet, but you're going from numbers to sets or vector spaces, and from vector spaces to something higher you want to go. And so what would be the next higher thing in this ladder? That would be a category. And we already see a category appear in this description, namely the derived category of coherent sheaves, or if you like, the category of perfect complexes. They're the same because X is smooth by hypothesis. And what is this? This you can very concretely think of as bounded cochain complexes of vector bundles on X. At least in the setting that I'm in, X is a smooth projective variety. It is true that perf X is just bounded cochain complexes of vector bundles. And this is an example of a triangulated DG category. There's an obvious way in which you can make this into a DG category, because if I have two cochain complexes, there's a natural cochain complex of maps between them. There's only one obvious thing you can write down. And so this forms a DG category. Okay. Now, in fact, in the topological examples I wrote down earlier, this is an algebraic geometry example. In the topological examples, also there are categories sitting around in the background. Namely, so let me, I'll come back to the bottom here, but let's go over here. So if X is a path-connected topological space, then I can form this category. And remember my convention that mod means kind of the enhancement of the derived category. So this is like some spectral version or DG version. So the homotopy category of mod R is the derived category of R. So this is like, it's not literally modules in the usual algebra sense, but this is like DG modules, suitably localized at quasi-isomorphisms. So to any path-connected topological space, I can associate a DG category, namely modules, over chains on the base loop space of X. Take some base point and take the loop space of X at that base point, and you can take chains on that. Because the loop space is an E1 algebra, there's a multiplication on the loop space. Chains on the loop space is also an algebra, an associative algebra, or a DG algebra. And modules over this is a DG category, localized at quasi-isomorphisms. So I have a DG category sitting around in the settings where I might want to talk about topological things like Poincaré duality. If M is a smooth manifold, of course, then this construction still applies, because M is also a topological space. But I can also describe a de Rham model for this, like something that is more differential geometric in flavor. Namely, I can associate a category C de Rham of M whose objects are cochain complexes of C infinity vector bundles with flat connections. So connection nabla that squares to 0. And for two vector bundles, the mapping complex, the chain complex of maps, is the differential forms with values in the mapping vector bundle, form EF, with a differential D, which is the obvious differential that is induced by the two connections and the de Rham differential. Okay, so there's only one natural thing you can write down here. I don't want to spell it out because I'm not going to use the formula in this talk, but there's one natural thing you can write down. So for smooth manifolds, I have this category. Similarly, for just to give another example from a different area of mathematics, if I have a symplectic manifold, for those of you who know what a symplectic manifold is, actually I can probably just say the definition. A symplectic manifold is a smooth manifold of dimension 2D with a closed form omega, 2 form omega, which is non-degenerate. So given such an object, you can associate to it something called the derived Fukaya category, whose objects are Lagrangian submanifolds of the symplectic manifold, and whose morphisms are computed by Lagrangian floor theory. Now, the reason I just wanted to throw this example in is because there is a duality of a different order of things, like a sort of much deeper kind of duality, the kind of thing that physicists would call a duality, called mirror duality between these type of categories, derived categories of coherent sheaves or perfect complexes, and categories associated to symplectic manifolds. So it turns out that for any reasonably nice algebraic variety, smooth projective variety, you can associate a symplectic manifold, some other symplectic manifold, such that the derived category of coherent sheaves on it is dual to, or in other words, equivalent to the derived Fukaya category of the mirror symplectic manifold. So I just want to throw that in for fun because it's a sort of much, it's an order of difficulty higher to formulate and prove this type of duality between one area of mathematics and another area of mathematics. But this is the kind of thing physicists play around with all the time when they say that two physical theories are dual to each other. They often turn out to mean that you have a duality between very different, from mathematical perspective, very different looking objects. So different that they live in sort of different areas of mathematics where traditionally people didn't talk to each other so much. And this duality, and the point I want to make is that this duality can be expressed as an equivalence of triangulated DG categories. So the whole idea, the unifying framework, I'm sort of trying to build towards a unifying framework for some of these dualities. And in all of these dualities, triangulated DG categories are going to play an important role. And you've already seen them a lot in this winter school. If you are an algebraic topologist, you might want to work with categories enriched in spectra instead of enriched in chain complexes. but the flavor of the mathematics and the formal structure of the results is quite similar. Okay, so moving on. Okay, any questions at this point? Maybe I should take questions. Okay, so now we have a bunch of examples, and we see that in each case I have a DG category. So now I just want to quickly mention an example of a different flavor, seemingly different flavor, and hopefully next time, time is the main constraint here, but hopefully next time I'll say a few words about how this is also related to the other dualities. So there's this thing called causal duality, and rather than give the formal definitions, let me start by sort of describing an example, which is very interesting for many reasons. So let's fix a field K, complex numbers if you like, and let's consider this algebra K epsilon, where epsilon is a variable in degree 1. And if I ask this algebra to be commutative, that automatically implies that epsilon squared is 0. But I'm actually just viewing this algebra as an associative algebra. So let me spell out that epsilon squared is 0. Then we have this other algebra, which is Ku with u in degree 2. So it's a polynomial ring with u in degree 2. Okay. Now, what's the relation between these two algebras? Exercise. B is just the mapping spectrum or the mapping cochain complex, R hom from K to K in the category of K epsilon modules. So you can compute this with all the technology that's been developed in this winter school. You take a resolution of K and then calculate the usual mapping space from the resolution to K, and you'll find that this is Ku. And so here I'm just reminding you that my notation map underline is just R hom. So now this is an example of two E1 algebras being causal dual. A and B are causal dual, and essentially, this equation here is telling you what it means for them to be causal dual. Now, this is a statement at the level of algebras, but why might you be interested in this statement? Because it might give you different ways of thinking about modules over K epsilon, for example. The relationship between these two algebras will induce a relationship between the representation theories of these two algebras. Namely, you have an adjunction of categories from mod A to mod B. In one direction, it's the mapping space, sorry, mapping complex, so underline. Oops. Page 5. This is the mapping complex. So you have the mapping complex from K to blank, mapping mod A to mod B. And you have an adjoint functor to that, which you can, I could have left it as an exercise. You can figure out the adjoint once you know that it exists. So actually, the existence of the adjoint is a formal consequence of the fact of the adjoint functor theorem, because this mapping space preserves all limits, and these categories are presentable. But then you can also explicitly compute the adjoint. Right? So you have this adjunction of categories, and now you can compare. You can go between two descriptions. You have now two descriptions of modules over K epsilon. One is modules over K epsilon, and the other in terms of modules over Ku. Now, in fact, the story is an algebraic incarnation of something that has a topological meaning. K epsilon is cochains on S1, and Ku is cochains on BS1, classifying space of S1, which is CP infinity. And this adjunction is an algebraic incarnation of the adjunction between spaces with an S1 action and spaces living over S1, spaces with a map to S1. Namely, if I'm given a space with an S1 action, taking homotopy S1 fixed points will give me a space. If I have a space X with an S1 action, I can send it to. So X maps to a point, so I get a map from X homotopy S1 fixed points to point with homotopy S1 fixed points. And homotopy orbits of the S1 action on a point is by definition BS1. So this thing is BS1. So starting from X, I get a space that lives over BS1. And similarly, if I start with a space over BS1, by looking at the base loops at a point and how it acts on the fiber, you get an action. You get a space with an S1 action. And that's the adjoint functor.
Pranav, at the expense of interrupting your talk, let me just say that they've actually seen a proof of this causal duality, because K is a small object in D of mod A, a proxy small object. This is a special case of the Dwyer-Greenlee's correspondence if one wishes
Right,
to see
great.
it that way.
Thanks for pointing that out. Yeah, so you have already seen this example in Shrikant's talks. Thanks, Shrikant. So moving on, this is part of a general theory. So if you start with an augmented associative, say, by associative here, I mean DG associative algebra, or if you're working in spectra or something, I mean something like an A infinity algebra or an E1 algebra, which is both the same thing. So you start with an associative algebra, then you can form, if it's augmented, that means K becomes an A module. So I can form K tensor AK. And all my constructions are derived. So this is a derived tensor product. And how can you compute this derived tensor product? You can write this as, if you like, the geometric realization of a simplicial object called the bar construction. Okay, so actually, I don't want to get into the details today, but I just wrote that down here. If there is time tomorrow, in my next talk on Saturday, I'll explain what this is. It's some sort of version of the nerve of a category. Something, yeah. So the bar construction is basically a way to compute K tensor AK. So it's an explicit simplicial object that computes this, whose geometric realization gives you this derived tensor product. And this thing is naturally a coalgebra. It's an associative coalgebra, which you might call the E1 Koszul dual coalgebra. And as you know, you can show that you get an adjunction formally between modules over A and co-modules over this bar of A. Now, if you have some finiteness conditions on A, then you can dualize bar A to get an algebra B. The dual of a coalgebra will be an algebra if you have finiteness conditions on A. And this thing is called the Koszul dual algebra. And you get an adjunction between mod A and mod B. And this restricts to an equivalence of infinity categories between suitable, between subcategories of mod A and subcategories of mod B, which satisfy some finiteness conditions. I don't want to get into those technicalities. It's actually quite technical. And there's an exhaustive work due to Pozitselsky analyzing, exactly what finiteness conditions you can put and, different variants of the derived category that you get on the other side. So I'll refer you to Pozitselsky for the details of the most, I think, up-to-date version for associative algebras, DG algebras. There's a further generalization of this to Koszul duality for EN algebras. And maybe next time I'll talk about this. But the key point I wanted to make, the claim I wanted to make, is that Poincaré duality is in fact an incarnation of Koszul duality. Okay, so that might seem like a very mysterious statement because I'm talking here just about algebras. And I'm suddenly now talking about that being related to something about manifolds. And the point I want to make is that the very definition of algebras are tied so closely to manifold theory that usual Poincaré duality turns out to be a special case of Koszul duality if you formulate things suitably. And this is due to work of Ayala and Francis. I mean, it's not a claim due to them, it's a theorem due to them. So this is a theorem Ayala Francis. I'm making a claim in the context of these talks. Francis, and maybe I should also mention Lurie and others. Lurie, I don't know, Salvatore, and there are many people whose ideas led up to this work, but I think Ayala Francis, sorry, I'm not written right, gave the definitive proof of this statement. Okay. So good. Okay, so it's 5:45 almost. Now the question is, how much time do I have? Do I have 5 minutes or?
Yeah, but that talk will be until 6 o'clock, right? But yeah, you can take 5 minutes, then 10 minutes for question answers. So yeah, whatever you feel like.
Okay, thanks. I mean, because formally, I think it's supposed to be 45 minutes, but I think we have, as a tradition, we have started going over that. So maybe I can.
It's a rule respected only in being broken.
Right. So, okay, so great. Then I can take a few minutes to say where we're going. Okay, so I just want to say a few things. So now I want to talk about DG categories. Maybe this should be yellow. So DG categories. So what do DG categories form? To understand statements about DG categories, we would like to understand what do DG categories form. This is a question that was asked long ago and has been studied by many people. But now with all this technology, I can give the answer. They form an infinity 2 category. So DG cat, I might work with triangulated ones, forms an infinity 2 category. Why? Because remember, an infinity 2 category, an infinity n category, is a category enriched. This is not a formal definition. This is just like the heuristic. Is a category enriched in infinity n minus 1 categories. Right? So given two DG categories, I need to give you an infinity 1 category of functors between them. So it turns out this is, I guess, originally due to work of Toen. So Toen. So, well, first of all, Tabuada proved that there's a theorem due to Tabuada is that there is a cofibrantly generated model structure on DG categories with equivalences being, weak equivalences being the Dwyer-Kahn equivalences, which I described earlier. So you can use this model structure to do things like derive the tensor product, right? So DG cat as a 1 category, DG cat is a symmetric monoidal, closed symmetric monoidal category. And you can use the model structure So I think there's only one obvious way to write down the tensor product, and then the internal hom is determined. So that's an exercise. So maybe I should say exercise is to formulate this. I've given references in my previous notes, so you can always look it up. But there's only one way to write this down, and it's straightforward. So I'll leave that to you, to the students. Okay. So so we can use the model structure to derive, to write down, to compute the tensor product. And so you get a derived tensor product, and then Toen gave a description. So there's a theorem due to Toen. It says the following, that the homotopy category of DG categories, or I use the notation H, but anyway, with the derived tensor product is closed, which means that there exists, so for all CD in DG cat, there is R hom CD also in DG cat, such that maps from E, some other DG category, to R hom CD is maps from E derived tensor product C to D. Again, I'll drop the derived from now on because I'll always be working the derived setting, but I just wanted to mention this because I'm talking about one categorical model here, so I have to distinguish between the ordinary tensor product in the underlying category and the derived tensor product. So this R hom CD is itself a DG category. You can think of a DG category as an infinity 1 category if you like. And by forgetting the k-linear structure, as I mentioned last time, so between any two objects in DG categories, I have an infinity 1 category of homs. So this is really an infinity 2 category. Okay. And if I'm given any infinity 2 category, I can form what is called its homotopy 2 category. So if let's say X is an infinity 2 category, or if X is, let X be an infinity, let X be an infinity 2 category, then you get H less than or equal to 2 of X to distinguish it from HX. So this will have objects equal to the objects of X. Then for X, Y in objects of C, the mapping space, now the maps between X and Y should be a category, because I'm trying to construct, this is a bicategory. H less than or 2 of X is going to be a bicategory. And it's defined as follows. So it's the obvious thing you'd think, the maps from X to Y is the homotopy category of, this is a maps, H less than or equal to 2 of X. This is the homotopy category of maps from X to Y in X itself. Okay. So from any infinity 2 category, I can extract a bicategory by passing to the homotopy categories of the mapping categories, the mapping infinity 1 categories, right? So I get a bicategory. So we will be interested, we will be interested the bicategory, let's say B, which will be the homotopy 2 category of the infinity 2 category dg cat k, okay, where here dg cat k is viewed as an infinity 2 category. So that's what I want to study. I just want to comment that there's a relationship between algebras and categories that is very important. So I want to give you another example of a bicategory. So this is one example. Maybe this is example 1 of bicategory that we're interested in. Let me say example 2, which would be very closely related, so it's almost the same thing. So let's take the Morita category. So the Morita category, its objects. So let's call this alg is this Morita bicategory, Morita infinity 2 category. It's defined as follows: the objects of alg are alg k, let's say. These are E1 algebras over K, so associative algebras. And the mapping, so for A, B algebras, the mapping space, the mapping category, the mapping infinity 1 category, A, B, is bimodules A, B. And this is an infinity 1 category. Recall, everything is derived from me, so these are DG algebras, if you like, or associative ring spectra. And these bimodules are also understood in the sense of, DG modules, and I'm localizing at quasi-isomorphisms or weak equivalences of spectra. And so this is an infinity 1 category. And so this gives rise to a H less than or equal to 2 of alg k. This is now a bicategory. Okay, so I want to study these bicategories. Now, what's the relation between these two bicategories? There is a functor from algebras, alg k, to, let's call it cat k, if you like dg cat k. Maybe I'll just write cat k. So let's just say cat k is now dg or spectral categories. Okay, so whatever you like. So cat k is equal to dg cat k if k is an ordinary ring, or hk spectral categories. If k is general ring spectrum. So there's a junction alg k to cat k. Well, let me write it like this. There's cat k star, which is pointed categories, and there's cat k, and there's a functor here which takes an algebra A to mod A together with the object A. So these are pairs C, E, with E belongs to objects of C. Okay, so these are pointed categories. And so I can go from algebras to pointed categories. And the nice thing is that you can also go the other way. So given a pointed category CE, you can go to endomorphisms of E, derived endomorphisms. And this is an algebra. Right? I think I'll have to polish this. It's not written too neatly. So the point is that there are functors this way, and by just forgetting, this vertical arrow is forgetful functor. So this is, so maybe I should just write it like this. Vertical arrow sends C, E goes to C. Okay. So in the end, what do I get? I get a functor from alg k to cat k. And so I can view every algebra as a category. But also if I have an algebra, if I have a category with a chosen object, I get an algebra. Now here's a theorem, and I'll stop with that. So definition, first of all. An object E in C is a compact generator if one E is compact maybe I should just say E is a compact object. E is small or compact, same thing. E is a compact object. And two, if mapping space from E to something else is contractible, then E is zero, is a zero object. Okay, so
F.
Huh?
F is the zero object.
Oh, sorry, F is a zero. I'm sorry. Thank you. Okay, so here I'm in a triangulated DG category. So this is a triangulated, whatever, DG category or stable infinity category. Let's say stable infinity category. Because I don't need any K-linear hypothesis. So then the theorem is the following. Is that if E is a compact generator, then the functor F goes to maps from E to F, which sends which goes from C to modules over end E is an equivalence. So this, I don't know who this is, a sort of folklore, I guess. I don't know who it is due to. It's known to, I mean, it's been known for a long time, and I've never seen it really attributed. And
Well,
sorry?
Keller had some version of it, where
Yeah.
algebraic triangulated categories being DG categories.
Yeah, I've definitely seen in Keller. So I don't know if that was the original or whether,
I don't know.
Yeah. And so maybe I'll just stop with one last theorem, which maybe will tell you why the algebra way of thinking about things is quite powerful. This is due to Bondal-Vandenberg. Is that if X is a quasi-compact, quasi-separated scheme, then the derived category of quasi-coherent sheaves admits a compact generator. So the corollary, the slogan here is that all spaces, all schemes, all QC, QS schemes are affine, are DG affine, are DG non-commutative affine. Okay, I'll stop there. That's basically saying that from the point of view of non-commutative geometry or non-commutative algebras, all schemes are actually affine. So you might as well just study DG algebras. And I'll try to, so that's the relation between the 2 points, the point of view using categories and the point of view using algebras. They're not that far from each other. So I should really stop now.
Thank you. Thank you, Pranav.